Welcome back to our CISSP study group. I'm B-Dubs, and today we're going to explore some exciting material together. Whether you're actively studying for the CISSP or just curious about cybersecurity, you're in the right place. Your dedication to learning is what makes these sessions special, and I'm thrilled to explore these topics with you. For those who missed our last deep dive into Domain 3 Objectives 3.1 and 3.2, don't worry. There's a complete playlist waiting for you to review at your own pace. I'll share that link in chat right now. Today we're tackling two crucial objectives. 3.3, select controls based upon system security requirements, and 3.4, understand security capabilities of information systems. Alright, picture this. You're at the airport and your laptop vanishes. Poof. It's got your emails, your projects, maybe even that embarrassing photo from last year's holiday party. How does it stay safe out there in the wild? That's what we're diving into today. Security controls and capabilities. The heroes keeping your data locked down. By the end of this session, you'll understand how to pick the right controls for any system and understand the built-in features that protect your systems from threats. So grab your monster or coffee, no judgment, and let's get rolling. First up, we're hitting Objective 3.3, selecting security controls based on what your system needs. This is important because your security controls need to align with both your technical requirements and business objectives. Think of it like packing for a trip. You wouldn't bring a snorkel to a ski lodge, right? Similarly, a bank needs much stricter access controls than a local coffee shop. Different systems need different tools, and we'll explore frameworks like NIST and ISO that will guide us through these choices. We'll walk through what controls are, how these frameworks help us make smart decisions, and most importantly, how to pick them. This part is all about getting the right gear for the job. So what exactly are security controls? They're your system's bodyguards, tools and processes that help protect against threats. Understanding these controls is crucial for building a strong security program. We went over the 7 major types of controls back in Domain 1 during Session 5, but if you remember, there was 3 main types of controls that when combined together to mitigate a single risk, created what is known as a complete control. Let's refresh on those 3 main types. Preventative controls stop an incident before it happens. Think of a firewall. It's like a locked gate, keeping unauthorized users out of your network. No key, no entry. Other examples include access control lists, data encryption, and security awareness training. Detective controls catch trouble in the act. An intrusion detection system, or IDS, is like a security camera. It spots suspicious activity, like someone poking around your server, and sounds the alarm. Other key examples include security audit logs, system monitoring tools, and antivirus software. Corrective controls fix things after an incident. Imagine malware trashes your files. Restoring from a backup is your corrective control, like calling in a cleanup crew after a storm. Additional examples include incident response procedures and disaster recovery plans. These 3 work together to protect the CIA triad: confidentiality, integrity, and availability. When implementing controls, organizations face common challenges. There might be budget constraints, balancing security needs with available resources. There could be user resistance, ensuring controls don't hamper productivity. And there might be technical limitations, integrating controls with your existing systems. Remember, security controls aren't just isolated tools, they're part of a broader risk management strategy. The selection of controls should be based on thorough risk assessments and follow the principle of defense in depth, using multiple layers of protection. Now, how do we organize all of this? That's where the frameworks come in. Picking controls from scratch is a nightmare. Luckily, we've got frameworks to help guide us. These are like playbooks for security. The NIST SP 853 is the gold standard for US federal systems. It's an entire control catalog that's detailed, with controls for everything from passwords to physical security. For example, a government agency might use NIST Access Control Family to set up multi-factor authentication and role-based access. Remember that while NIST may be a requirement for US federal systems, many other organizations will voluntarily follow the NIST standards as they're incredibly thorough and freely available to anyone. ISO 27001 and 27002 is a global favorite, perfect for multinational companies. It's flexible and risk-focused. Imagine a European company expanding to Asia. ISO 27001 provides a consistent security approach across all locations, and then ISO 27002 provides the guidance for implementing the controls within the ISO 27001. The controls objectives for information technologies, or COBIT, was created by ISACA, and it bridges the gap between technical security and business goals. Picture a CEO asking, "Are we secure?" COBIT helps translate the security metrics into business value. The Information Technology Infrastructure Library, or ITIL, focuses on secure IT service delivery. Think of a bank's IT help desk. ITIL ensures they verify identities before resetting passwords or granting access. And the Payment Card Industry Data Security Standard, or PCI DSS, is essential for anyone handling credit cards. An e-commerce site must follow PCI DSS to protect customer payment data. Beyond these frameworks, security professionals should be familiar with COSO for Enterprise Risk Management, HIPAA for Healthcare Compliance, FISMA for Federal Systems, FedRAMP for Cloud Services, and SOX for Financial Reporting. Most organizations will choose to use multiple frameworks to meet their unique regulatory and business requirements. For example, a government contractor building cloud solutions might choose to implement the NIST 853 combined with FedRAMP. A global retail chain handling credit cards might implement ISO 27001 alongside the PCI DSS. And a modern healthcare provider with online billing might implement a combination of HIPAA, ISO 27001, and PCI DSS. So here's where it gets interesting. Organizations don't treat these frameworks as separate rulebooks. Through a process called rationalization, they create a unified security program. Think of that healthcare provider mapping HIPAA privacy requirements to ISO 27001 controls and then layering in PCI DSS for secure payment processing. The smart move is to map overlapping controls between frameworks. When NIST and ISO both call for strong passwords, you implement one robust password policy that satisfies both. It's efficient security in action. So when we are rationalizing frameworks, first we need to identify which specific regulations and requirements the organization needs to follow. This helps narrow down which frameworks you'll be working with. Next, we map the controls across the different frameworks to find any areas of overlap, kind of like matching socks out of the dryer. This allows us to identify duplicate or redundant requirements. With the overlapping or duplicated controls identified, we can then merge and consolidate these similar requirements into a single streamlined set of controls. Finally, we customize the implementation of the rationalized framework to best fit the organization's specific needs and constraints. The overall process is about taking a strategic, structured approach to aligning multiple security standards in a way that reduces complexity and overhead for the organization. Think of it as decluttering your security program. You're taking all these different standards and turning them into one smooth, manageable system that doesn't drive everyone crazy with unnecessary complexity. Work smarter, not harder, right? Now let's explore another powerful tool we discussed in the last session, the Common Criteria. You might remember the Common Criteria, or CC, from our last session. It's a global standard for evaluating IT security products. Thanks to the Common Criteria Recognition Arrangement, or CCRA, certification in one country is recognized by other participating nations, making it truly international. Let's do a quick refresh. First, a protection profile is basically the buyer's wish list. For example, a government agency might require all laptops to have full disk encryption, secure boot, and biometric authentication in their PP. Or if you need a firewall, it might list block unauthorized access and log all traffic. That's your PP. Then, security targets are the vendor's pitch. Take Windows 11. Its ST demonstrates how BitLocker encryption and Windows Hello biometrics fulfill laptop security PP requirements. Or when firewall vendors say our firewall uses stateful inspection to block access and logs everything in real time. That's the ST, proving they meet your protection profile. And then evaluation assurance levels show how much testing was performed. EAL1 is the basic testing, like a quick glance, and EAL7 is far more intense, like a full audit. Most commercial products are certified at EAL4. It strikes a sweet spot with methodical design and testing without breaking the bank. Military systems often require EAL6 or EAL7 for maximum security assurance. Last time, we covered the basics. Today, we're applying it. So how do you actually use the CC to pick controls? Let's use a real scenario, securing a bank's payment system, where confidentiality is everything. First, you need to assess your needs. What's at stake? For the bank, it's transaction data. Risks include breaches or leaks, so you need strong access controls and encryption. Then find or write a protection profile. Grab one for payment systems off the shelf, or tailor one to meet your needs. It might demand encrypt all transactions and restrict access to authorized users only. Then you match that to a security target. You find a product where the vendor's ST aligns. Maybe a firewall's ST says, we encrypt with AES 256 and use role-based access. Bingo, that fits. Finally, pick an EAL. How much assurance do you need? A consumer smartphone might be tested at EAL 2 to 3. An enterprise firewall might be tested at EAL 4. And military systems would be more on an EAL 6 to 7 level. For our bank example, EAL 4 or higher ensures the product's been battle tested and not just rubber stamped. So you land on an EAL 4 certified firewall, proven to encrypt data and block threats. The common criteria makes this systematic and not a wild guess. Now let's shift gears to see what's actually built into your systems. We're moving into exam objective 3.4, understanding security capabilities of information systems. These integrated defense mechanisms form the backbone of modern system security. Think of them as layers in a castle's defense, each playing a crucial role in protecting your digital assets. We're talking about more than just memory protection or encryption. We'll explore how everything from the CPU to the software works together to keep the threats out. We'll kick off with big picture ideas like the reference monitor concept and the trusted computing base. Then we'll get into the nitty-gritty, CPUs, storage, middleware, and more. Along the way, we'll see how privilege levels and defense in depth make the whole system tougher to crack. These capabilities don't work in isolation. They form an interconnected security mesh that aligns with frameworks like NIST and ISO 27001. So let's lay the groundwork with 3 core ideas that work together: the reference monitor concept, the security kernel, and the trusted computing base. These form the foundation of system security, each building upon the other. First, we have the reference monitor concept, or RMC. Think of this as the ultimate gatekeeper. Every time someone or something like an app wants access to a file or resource, the RMC steps in. It's like a bouncer at a club, checking IDs against a list of rules. Allowed? You're in. Not allowed? Beat it. It also logs every attempt. The RMC must have 3 essential properties. Tamper-proof, meaning it cannot be modified by unauthorized entities. Non-bypassable, meaning it's always running and checking every access attempt. And verifiable, or simple enough to be tested and validated. Then we have the security kernel. This is the RMC brought to life. The RMC is only a concept, but the security kernel is the actual hardware or software enforcing those access rules. Remember that the security kernel is the actual implementation of the reference monitor concept. In modern operating systems, this is implemented through kernel mode or privileged and user mode or restricted operations. A solid security kernel is complete, where every access goes through the kernel, isolated or locked down so only authorized changes are possible, and verifiable, meaning we can audit it to ensure it's doing its job. And finally, we have the Trusted Computing Base, or TCB. This is the whole security team. Every bit of hardware, software, and firmware that keeps the system safe. Imagine a castle's full defense: walls, guards, and even the rulebook. In a company, the TCB covers CPUs, memory, policies, everything. If the TCB fails, the castle falls. Security best practice is to keep the TCB as small as possible. The less code there is to secure and verify, the better. These ideas set the stage. Now let's zoom into the hardware, starting with the CPU. The CPU isn't just the system's brain, it's also a security enforcer. Think of it as a building with different security levels. Here's how it maintains security. Let's start with what does it do? The CPU runs a loop, fetching an instruction, decode it, execute it, and store the result. But its crucial security role is deciding who actually gets to do what. CPUs have built-in modes to control access and provide privilege levels. First is the kernel mode, known as the supervisor state. This is full power, like a system administrator with complete access. The operating system's core runs here. Then there's user mode, known as the problem state, because this is what the CPU does. It solves problems. This mode provides limited access like a regular user account. Your everyday applications run here, preventing them from accessing critical system resources. Think of it like a company's security system. When you need to install software, it's like requesting a temporary security badge to access restricted areas, or elevating privileges. This separation ensures that if a regular program crashes or gets infected with malware, it can't just compromise the entire system. Just like how hopefully an intern's mistake shouldn't be able to shut down the whole company. CPUs traditionally use a ring model for security layers, known as the ring protection model. Ring 0 is the kernel's home, the most privileged ring where the core operating system runs. On the other end of it, we have Ring 3, which is where your applications run, least privileged for maximum security. Rings 1 and 2 are typically used for things like your libraries and your drivers. This privilege hierarchy is crucial for security. Malware running in Ring 3 can't easily escalate to Ring 0 to take control of your system. Any communication between rings must go through strictly controlled channels called system calls, creating a secure barrier between user applications and critical system functions. Modern systems have evolved this model even further, with virtualization introducing additional security layers through hypervisors. This separation is crucial because many cyber attacks specifically target privilege escalation, trying to break out of user mode restrictions to gain kernel-level access. Now let's dive into memory protection, a critical security feature that prevents applications from interfering with each other. Imagine your computer as a busy office building. Without memory protection, it would be chaos. Any program could walk into any other program's office and mess with their files. In your web browser, you've probably noticed that when one tab crashes, the others keep working. That's memory protection in action. And here's how it works. First, there's process isolation. Think of this like giving each application its own private office. The CPU and Memory Management Unit, or MMU, work as security guards, ensuring each application only accesses its assigned space. This is especially important for technologies like virtualization and containers. Imagine you have two applications running, a browser and a spreadsheet. Should the browser see your spreadsheet data? No way. Process isolation keeps them separate. Without this process isolation, a glitchy application could crash everything or steal data. It's like traffic lanes. Stay in your lane and we all get home safe. This fundamental security principle ensures that even if one application is compromised, the others remain protected. And then we have memory segmentation, where the CPU and MMU carve memory into chunks, physically separating applications, like having different floors in our office building. Each program gets its own floor, preventing malicious code from breaking into other areas. With time division multiplexing, the CPU juggles applications by giving each a tiny time slot, like milliseconds, to run. The operating system scheduler manages this process, deciding which application gets CPU time and for how long, like a traffic controller. It switches so fast it feels simultaneous, but each application is isolated in time, no hogging the CPU. Address Space Layout Randomization, or ASLR, scrambles your memory addresses every time your system boots. This is like randomly changing office locations every day. Even if an attacker knows there's something valuable in the building, they won't know where to find it. And Data Execution Prevention, or DEP, marks memory regions as non-executable. Think of this as having strict rules about where work can happen. Just like you wouldn't cook in your office, DEP prevents code from running in data-only areas. Finally, virtual memory uses both RAM and disk space to handle program data. When RAM gets full, some data moves to a temporary file on the disk called the swap space. It's important to note that this swap space needs encryption, or attackers could steal sensitive data from it. The Memory Management Unit, or MMU, acts as our building's security system. It maintains detailed records of which program can access what memory, checking permissions for every single request. Do you remember the Heartbleed vulnerability from 2014? That's what happens when memory protection fails. Heartbleed exploited weak memory protection in OpenSSL, which allowed attackers to read sensitive data from other programs' memory space. The same principle applies to classic attacks like the Morris worm, which is a buffer overflow attack. Now let's look at another crucial security component, the TPM. The Trusted Platform Module, or TPM, is a specialized security chip that is physically built into your system, and it serves as a hardware root of trust. The current standard is TPM 2.0, which is a dedicated chip that securely stores and generates cryptographic keys, protecting them from software attacks. The TPM acts like a secure vault, built right into your computer. Imagine having an ultra-secure safe that only your system can access. This chip is specifically designed to resist both software-based attacks and physical tampering attempts. Let's look at the key features that make a TPM so valuable. First, there's secure boot. Think of this like a DNA test for your system. Before anything starts up, the TPM verifies that nothing has been tampered with. It uses special registers called Platform Configuration Registers, or PCRs, to keep track of your system's state. Next is key storage. The TPM provides a fortress for your encryption keys. Even if an attacker gets physical access to your device, they can't extract these keys from the TPM. Then we have data binding that locks data to that specific device. Steal the hard drive? Good luck. It's useless elsewhere. Data sealing encrypts data and only unlocks it when the system is in a known, safe state. If something's off, that data stays sealed tight. And finally, there's remote attestation. This feature allows your device to prove to other systems that it has not been compromised. It's like having a built-in lie detector for your system's integrity. So how does this work in the real world? If you're using Windows with BitLocker, it uses the TPM to protect your drive encryption keys. If someone tampers with your system, those keys remain secure. In enterprise environments, the TPM is crucial for device authentication. IT departments can verify that only trusted devices are connecting to their networks. Cloud providers rely on TPM attestation to ensure their clients' endpoints have not been compromised. TPMs are now everywhere, in laptops, servers, and even IoT gadgets. Imagine a smart thermostat. The TPM ensures no one slips in a rogue update. Pair it with memory protection, and you've got hardware security on lockdown. The TPM is fundamental to establishing trust at the hardware level. Now let's move on to discuss encryption and decryption. Encryption and decryption protect our data, both at rest with stored files and databases, and data in transit, like emails and web traffic. Encryption transforms your data into a secret code that only authorized parties can unlock with decryption. First, let's understand encryption. It's the process of converting readable data in an unreadable format, using a special key. Think of it like putting your message in a locked safe. Decryption is the reverse, using the correct key to convert that scrambled data back into its original readable form, or unlocking that safe. We also have hashing, which is different. It creates a unique fingerprint of data that cannot be reversed. This is perfect for verifying file integrity or storing passwords. There are two main types of encryption: symmetric and asymmetric. Symmetric encryption uses the same key for both locking and unlocking. It's fast, efficient, and perfect for encrypting large amounts of data. Asymmetric encryption uses two different keys: a public key to encrypt and a private key to decrypt. It's slower, but excellent for secure communications. A great way I've memorized the differences in these two is remembering that symmetric encryption has symmetry, which means it's the same on both sides, or it uses the same keys. Asymmetric encryption is the opposite, with two different keys, the public and private pair. We also have hybrid encryption, where systems utilize asymmetric encryption to exchange symmetric encryption keys securely. Some examples of encryption include VPNs that use symmetric encryption to protect your internet traffic. HTTPS websites use asymmetric encryption for secure connections, and password storage relies on secure hashing algorithms. It's important to follow security best practices for your encryption keys. This includes regular rotation to keep your keys fresh and secure. Backup procedures ensure you never lose access, and proper key lifecycle management from creation to retirement. And hardware security modules, or HSMs, provide the ultimate protection. Remember, encryption is just one layer of your security strategy. When combined with TPM and proper memory protection, you create a robust defense for your data. As a side note, we'll dive much deeper into encryption in our next session, so this is just a high-level overview today. Then we move into hashing. Hashing is all about integrity. It's like a DNA test for your data. When you run a file through a hash function, you get a fixed link message digest, or fingerprint, that's unique to that data. Common algorithms include SHA-256, which is today's standard. SHA-3 is the newest, and MD5, although now it's considered cryptographically broken. Change one comma in your file, and the hash changes completely. That's how we detect tampering. It's fast, one way, meaning you cannot reverse it. And strong algorithms are collision resistant, meaning it's computationally infeasible for two different files to produce the same hash. When you're downloading software, you might see a hash value posted separately. Download the file, hash it yourself, and compare the two. If they match, your download is untampered. This same principle powers digital signatures and blockchain technology, where each block contains the hash of the previous block, creating an unbreakable chain. Unlike encryption, which scrambles data to keep it secret, hashing focuses purely on integrity. Together, they're a powerful duo. Encryption locks your data, while hashing proves it has not changed. Now, data needs a place to live, and systems use two main storage types, each with unique security challenges. We have primary storage, or volatile storage. It's fast, but it's temporary, like RAM or CPU cache. It holds data while the system is on, but if you shut it down, it's totally gone. While speed's the game here, it's vulnerable to memory scraping malware and cold boot attacks, where attackers freeze RAM to preserve data. Then we have secondary storage, or non-volatile storage. This is slower but permanent, like hard drives or solid-state drives. Your files and operating system live here. Safe, even when powered off, and modern solutions like BitLocker, Veracrypt, or self-encrypting drives provide strong protection. There's also virtual memory, which is a mix of both. When RAM is full, the system swaps data to a paging file on the drive. It's slower, but it keeps things running. Each storage type needs specific protections to maintain confidentiality, integrity, and availability. RAM needs protection from memory attacks and tampering, while drives need encryption and secure erasure capabilities. Newer technologies like NVMe drives even include built-in security features for hardware-level protection. It's all about keeping data safe wherever it sits. And then we have the system kernel. Think of the system kernel as your building's security control room. It's the operating system's command center where all critical operations are managed and monitored. While it's not the same as the security kernel we discussed earlier, understanding the difference is crucial. So what does it do? Like a control room operator, the kernel manages everything: CPU scheduling, memory allocation, storage access, and process management. It runs in privileged kernel mode with full access, making all the important decisions. System kernel architecture types include monolithic, where all services run in the kernel space. This is faster, but it has a larger attack surface. And then there's the microkernel with minimal core services. This is more secure, but it's slightly slower. If the system kernel is compromised, it's like giving an attacker the master key to every room. That's why modern systems use protective measures like driver signing requirements, where only certified, verified code can run at the system kernel level. So what's the difference in a system kernel and a security kernel? Think of it this way: the system kernel runs the OS operations, while the security kernel acts as the security guard, enforcing those reference monitor concept rules, and the security kernel is part of the trusted computing base, ensuring the system kernel stays within secure boundaries. Now let's move on to talk about middleware. This is the crucial software that connects different systems and applications. Think of middleware as a universal translator that helps modern and legacy systems communicate effectively. So what does middleware actually do for us? It performs several critical functions. It handles all the authentication and authorization, making sure that only the right users and systems get access. It transforms data between different formats, and it routes it to the right destination. It manages your APIs, controlling how different services interact, and it enables different services to work together seamlessly. But here's where it gets interesting from a security perspective. Middleware can be a target for several types of attacks. Attackers might try to exploit unsecured API endpoints. Man-in-the-middle attacks can intercept communications. Weak authentication can be compromised, and sensitive data might be exposed during transmission. To protect your middleware, you need a multi-layered approach. Implement strong access controls, encrypt all data in transit, maintain comprehensive logs, and regularly audit your security measures. Remember, middleware is part of your trusted computing base, so a compromise here can affect your entire system's security. And remember that one security control is never enough. Just like a medieval castle didn't rely on walls alone, modern defense in depth strategy layers multiple controls so that if one fails, others remain standing. Think of it as combining ancient wisdom with modern technology. Each layer prevents, detects, or responds to threats. If you remember the Target breach of 2013, hackers first compromised a HVAC vendor's credentials, bypassing vendor management. They moved laterally through weak network segmentation and accessed point-of-sale systems due to insufficient application controls. Proper defense in depth could have stopped them at multiple points. And think about the different layers you may have within your organization. You want to protect your risk at each of these layers. For example, at the physical layer, you could have security guards working with biometric access, surveillance systems, and environmental controls. At the network layer, you might have firewalls collaborating with IDS or IPS, network segmentation, and traffic monitoring. At the system layer, you could have memory protection and TPM working alongside secure boot and hardware encryption. And finally, at the application layer, you may implement multi-factor authentication combined with encryption access controls and security testing. Remember, these layers must work together seamlessly while being regularly tested and updated. It's not just about having multiple walls. It's about having walls that complement each other and adapt to new threats. Think cost-effective and not just comprehensive. After all, even the strongest castles need smart resource allocation to remain effective. Alright, let's wrap up today's session by reviewing the key concepts we covered about selecting controls and understanding security capabilities. First, we talked about security controls. Remember that when choosing controls, you need to look at your system requirements. What compliance standards do you need to meet? And most importantly, your risk assessment results. This helps you make informed decisions about which controls will be most effective. We then explored memory protection, a crucial technical control that keeps your system secure through process isolation and hardware segmentation. Think of it as building walls between different processes to prevent them from interfering with each other. The TPM, or Trusted Platform Module, was another key topic. This hardware-based root of trust is your system security guard, providing secure boot, data binding, and remote attestation capabilities. It's that extra layer of hardware security that many organizations rely on. We covered how encryption and hashing work together. Encryption keeps your data confidential, while hashing ensures it hasn't been tampered with. This applies whether your data is sitting on a server or moving across networks. And when it comes to storage, remember that different types, both volatile and non-volatile, need different security approaches. You can't protect RAM the same way you protect a hard drive. We also discussed the system kernel and middleware. These are like the traffic controllers of your system, and they need robust security measures to prevent unauthorized access or manipulation. And finally, we talked about defense in depth. Remember, it's not about having just one strong lock. It's about having multiple layers of security across physical, network, system, and application layers. Here's the key takeaway. When you're implementing security controls, always think about balancing three things: your security requirements, how usable the system needs to be, and what makes financial sense for your organization. Remember to think like a manager. Focus on risk-based decisions and how security aligns with business goals, rather than just implementing technical solutions because they're cool or new. Alright, that's it for exam objectives 3.3 and 3.4. Remember, you can always go back and rewatch sections, pause, and take notes. These sessions will remain on YouTube, so you can watch anytime. I'm also adding chapters after each live stream so you can revisit certain topics. This is one more step on your CISSP journey, and you'll find these concepts appearing throughout other domains we'll cover. Focus on understanding these core concepts and their real-world applications, especially from that management perspective. Keep studying, keep practicing, keep asking questions, and remember, every security professional started exactly where you are now. And don't forget, you've got this. Now it's time to start the after party. Join us in the Study GRC Discord server's CISSP voice channel for deeper discussions and to answer any questions you have. This is your chance to learn from others and build connections in the security community. If you're not in the Discord yet, you can go to cissp.britwhite.io for the Discord link. And don't forget to grab your CISSP role when you join, so you can find the dedicated channels. Next time, we'll be continuing Domain 3 after our live session on Tuesday, April 8th at 6 p.m. U.S. Central Time. Thanks for watching, and I'll see you in Discord.